All right, so thanks for watching this video on trigonometric identities. By the end of this video, you should be able to reproduce the three Pythagorean theorems. You should be able to reproduce the double angle theorem for the sine. You should be able to reproduce the three options for the double angle theorems for the cosine. And you should be able to use the above trig identities to prove equations are equivalent, or to simplify equations. So let's jump right into it. First, let me share with you the three Pythagorean identities that we have. The most famous, sine squared theta plus cosine squared theta equals 1. Copy that down. You need to memorize that. You need to know that, all right? And then there's two more. This second one here, tan squared theta plus 1 equals secant squared theta, comes actually from this one up above here, from sine squared theta plus cosine squared theta equals 1. And remember, theta is just some angle measure, right? So I could certainly write this as sine squared of x plus cosine squared of x equals 1, right? And it doesn't matter what the variable is. But a lot of times in trigonometry, we use theta to represent an angle measure. All right, so this second one here, the tan squared theta plus 1 equals secant squared theta, comes from sine squared theta plus cosine squared theta equals 1. Let me show you. If I divided both sides of this equation, or if I divided every single term by cosine squared, what would I get? Well, what's sine squared theta plus cosine squared theta? Tangent squared theta, right? Sine over cosine is tangent, right? You know that? Hopefully you know that. The tangent of any angle is the sine of that angle over the cosine of that angle. Hopefully you know that. Um, Hopefully you know that relationship, that trigonometric identity, that trigonometric rule. What's cosine squared theta divided by cosine squared theta? Well, anything divided by itself is 1. And what's 1 divided by cosine squared? Secant squared, right? That's a reciprocal function. All right, so copy this down. Tan squared theta plus 1 equals secant squared theta. You have to know that. You have to remember that. All right, and then there's a third one. This third one here, 1 plus cotan squared theta equals cosecant squared theta. All right, that is another one that comes from up above here. So let me just erase this up above here. And let me show you what happens if you divide both sides of this equation, or all three terms, by sine squared, right? Whatever you do to one side of the equation, as long as you do it to the other side of the equation, we're in business, right? So sine squared divided by sine squared is obviously 1. Cosine squared divided by sine squared, did you know, is cotan squared? Hopefully you knew that. Hopefully you knew that the cotan of any angle equals 1 over the tangent of any angle.
Good afternoon. For all the students that are interested in going into the bowling meeting this afternoon, the room has been changed. It's now being held in the main office conference room. That's the bowling meeting is in the main office conference room.
All right, so sorry about that. So what was I saying? This identity, 1 plus cotan squared theta equals cosecant squared theta, comes from sine squared theta plus cosine squared theta equals 1, right? And what is 1 divided by the sine squared? That would be cosecant, all right? Cosecant squared. So those are your reciprocal trig identities. All right, so those are three Pythagorean identities, we call them, but you need to know them, all right? Copy them down, memorize them. All right, so sometimes we use these Pythagorean theorems for different things, but I'm just going to basically show you that. What if I plugged in some random value for theta? What if theta was 30 degrees? Would this actually work? Well, it would work. You don't have to copy this down. But this is just me sort of showing you that, hey, what if I plugged in 30 degrees for theta? What's the sine of 30 degrees squared? plus the cosine of 30 degrees squared. Would that in fact equal 1? Well, yes, it would. No matter what value I put in for theta, it would work. What's the sine of 30 degrees? 1/2. What's 1/2 squared? 1/4. What's the cosine of 30 degrees? That's radical 3 over 2, right? What's radical 3 times radical 3? Well, that would be 3. What's 2 times 2? 4. What do you think? Does 1/4 plus 3/4 equal 1? You bet it does, right? You bet it does. So it certainly works, and it would work for all of these, right? If I wanted to plug in 30 degrees for theta in here, I'd get the same thing, all right? I would get, well, not the same thing, but whatever's on the left would equal whatever's on the right. So let me just show you. Again, this is nothing that you need to copy down. It's just sort of cool to see that, you know, when you plug in different values for theta, they're going to work. What's the tan of 30 degrees? Radical 3 over 3, right? Oops. What's the secant of 30 degrees? Oh, great question. That's a tough one. I don't know. If you don't know, don't worry about it, because I don't know what the secant of 30 degrees is either. But I know that the secant of 30 degrees is 1 over the cosine of 30 degrees, right? Now, the cosine of 30 degrees I know, but I'll get to that in 1 second. Let me come back over here to the left. Radical 3 times radical 3 is 3. 3 times 3 is 9. What do we have here? 1/3 plus 1. Isn't that, whoops, got a little ahead of myself there. Isn't that 4/3? Yes, it is. Is that 4/3? That's what's going on the right side. The question is it going to be what happens on the left side? Well, what's the cosine of 30 degrees? It's radical 3 over 2, all right? Now I'm going to need a little more room here because I've got 1 divided by a radical 3 over 2. So I'm going to keep, change, flip. All right, so I've got 2 over radical 3 now. So 2 over radical 3, guess what I'm going to do with that? I'm going to square it, right? Because I haven't squared it yet. What's 2 times 2? Well, that would be 4 up top. What's radical 3 times radical 3? That would be 3 on the bottom. Look at that. 4/3 does in fact equal 4/3. All right, again, I've sort of wasted my time here. You can fast forward through this if you want to, because it's not too applicable to what we're doing here, but it's sort of cool to see, hey, what happens if I were to plug in, you know, some value for theta. So let's go with 30 degrees. That's what we've been sticking with, right? What do you think? Will this equation get the same number on both sides? That's the question, and the answer is yes, it will. Let me show you how. So cotan is going to be 1 over the tangent, right? And that is going to be 1 over radical 3 over 3. By the powers of keep, change, flip inside there, I'm going to get that. All right, no need to rationalize that. Because when I, let me move this up here and get that out of the way a little bit. I don't know exactly what this is or why it's there. There we go. I don't know why that keeps showing up, but at any rate, 3 squared is 9. All right. Radical 3 times radical 3 is 3, and 1 plus 3, of course, is 4. All right. Let's see what happens on the right side here. What's the cosecant of 30 degrees? Well, that's going to be 1 over the sine of 30 degrees, right? What's the sine of 30 degrees? Well, that's going to be 1/2. By the powers of keep, change, flip, guess what's going to happen inside? I'm going to get 1 times 2 over 1, or 2, and 2 squared, of course, is 4. Look at that. They, in fact, are equal to each other. Kind of cool. Nah, not really. So let's move on. Let's talk about double angle formulas. So there's double angle formulas for the sine, cosine, tangent, even, secant, cosecant, cotan, but we're only going to deal with the double angle formulas for the sine and for the cosine. So first, copy this down, double angle formulas. And the first one you want to copy down is the sine of 2 theta. Okay, so the reason why we call it a double angle formula is because theta is the angle and you're doubling it. All right, and the formula is that the sine of 2 theta is the same thing as 2 sine theta cosine theta. Again, just something you need to memorize. All right. So there's your double angle formula for the sine of 2 theta. That equals 2 sine theta cosine theta. So this expression here, 2 cosine theta divided by the sine of 2 theta, what is it equivalent to? This is a multiple choice question. All right, make sure you have that double angle formula copied down. Make sure you have the sine of 2 theta equals 2 sine theta cosine theta because we're going to need it. All right, you ready? Well, let's do it. So let's see, up top here we have 2 times the cosine of theta. On the bottom, guess what we have? We have a double angle formula, the sine of 2 theta. So we can replace the sine of 2 theta with 2 sine theta cosine theta. All right? Once we do that, guess what? We can cancel the 2's and we can cancel the cosines. All right, so what's left? Looks like we have 1 over the sine of theta, all right? What do you think? Is 1 over the sine of theta one of the choices? No, it's not, but guess what? 1 over the sine of theta is the cosecant of theta. Huh? So there you go, choice 1. All right, so there's an example of how we use that double angle formula. What's the double angle formula that you need to know? Right up top there, the sine of 2 theta equals 2 sine theta cosine theta. All right, let me show you some options for the cosine double angle formula. The cosine of 2 theta, you actually have 3 different options. Yeah, you sort of need to know all 3 of these options. Sorry about that. The first one, the cosine of 2 theta, where you're doubling the angle. Again, that's why we call it a double angle formula. We're doubling the angle. Is cosine squared theta minus sine squared theta. So if for whatever reason you needed to maybe do some factoring, this is the difference of 2 perfect squares, right? Cosine squared theta minus sine squared theta. You might use this option. All right, a second option for you would be, whoops, didn't mean to have that happen, meant to go purple. The second option would be, what if you wanted to replace the cosine of 2 theta with something that just was in terms of cosines? Well, then you would use this one, 2 cosine squared theta minus 1. Believe it or not, that equals the exact same thing as the cosine of 2 theta. And what if you had the cosine of 2 theta and you wanted to represent it just in terms of sines? Well, then this would be your choice, 1 minus 2 sine squared theta. All right, so pause the video, make sure you have all 3 of those options copied down. You never know which one you're going to need. And let's do an example. The expression cosine squared theta minus the cosine of 2 theta. This is a double angle here, so we can use a double angle formula. So what do you think? I've got the cosine squared of theta minus, now be careful here, when you represent the cosine of 2 theta, we have to put it in parentheses, right? So do you have a preference? I don't know. We've got cosine squared. Why don't we go with cosine squared theta minus sine squared theta? You don't have to, but I think that might work for us, right? So if I replace the cosine of 2 theta with cosine squared theta minus sine squared theta, let's see what would happen. I get the cosine squared theta. When I distribute this negative here, I'm going to get minus cosine squared theta plus sine squared theta. And look at that. Look at what happened. These guys are gone. That's what's left. There's my answer. All right. All right, so one more thing I want to talk to you about is proving trigonometric identities. And now we're going to take these formulas that we were just working with. The Pythagorean identities, sine squared theta plus cosine squared theta equals 1. Tan squared theta plus 1 equals secant squared theta. And the third Pythagorean identity there, which is cotan squared theta plus 1 equals cosecant squared theta, right? So we're going to take those along with the double angle formulas, the sine of 2 theta and the cosine of 2 theta, those four formulas in essence, and we're going to try to prove these identities. So when you prove that an equality is an identity, we need to show that both sides of the equality can be written in the same form. Technically, what you want to do is you don't want to cross the equal sign. So a lot of times you'll see teachers or people put a line right where that equal sign is so that you don't cross it. All right, so just work on the left side or just work on the right side. So what do you want to do? You want to work on the left side or on the right side? It doesn't matter, believe it or not, as long as you can establish that whatever's on the left is exactly the same as what's on the right. All right, so I'm going to start on the left side, if that's okay with you, because I'm recognizing this. What's sine squared theta plus cosine squared theta? That's an identity, right? Isn't it? So I've got the tan squared theta plus sine squared theta plus cosine squared theta equals 1, yes? And let me ask you a question. Do you recognize this? Tan squared theta plus 1, what does that equal? Isn't that another Pythagorean identity? Doesn't that equal the secant squared of theta? Yeah, it most certainly does. Have we touched this left side? No, we have not touched the left side. We certainly could have if you wanted to. You want to write this as 1 over the cosine squared of theta? Sure, you can. And what are you going to do over here for the secant squared? You write that as 1 over the cosine squared. But as long as you have these guys equaling the exact same thing, and that's it. You have proven the identity. You have proven that they're equal to each other. All right, let me give you another example there. How about this second one? Prove that the cosine of theta times the secant minus cosine equals sine squared of theta. All right, so again, since we're proving these identities, let's sort of draw a line down the middle and make sure that we don't cross. And when I say we don't cross it, this is what I mean. If you're wondering, like, what the heck am I talking about? What if I divided both sides of the equation by the cosine of theta? Am I allowed to do that? Well, whatever you do to one side of the equation, that's okay as long as you do it to the other side of the equation, right? Yeah, that's correct. But you don't want to do that in these trig identity proofs. So you don't want to cross the equal sign. You just want to stay on one side of the equal sign and try to work with it. Try to simplify it. So what if I stayed on the left, and what if I just distributed this? Let's see what would happen. I'd get the cosine of theta times the secant of theta minus the cosine squared of theta. All right, whatever. What is the secant of theta equal to? Do you know? That's going to be 1 over the cosine of theta, all right? All right, so now when I take a look at this here, I can cancel those guys, and I've got 1 minus the cosine squared of theta, right? Now, I don't really know what else to do at this point. I sort of want to take a peek over here. I don't want to cross the equal sign, but I want to take a peek over here, and I want to see if I could set up a situation where the left side was the same as the right side. What do you think? 1 minus cosine squared. Does that look familiar at all? What about sine squared theta plus cosine squared theta equals 1? Could we manipulate that a little bit? What if I subtracted the cosine squared from both sides? What if I subtracted the cosine squared from both sides? What would I get? Now, listen, I'm off on the side here, right? You may say, Sipe, you just said that, we can't cross the equal sign. Yeah, that's true. I'm not doing the Pythagorean, or I'm sorry, I'm not doing the trig proof right now. I'm just sort of trying to replace 1 minus cosine squared. So if I take this trig identity and I subtract cosine squared theta from both sides, guess what I get? I get 1 minus cosine squared theta. Look at what 1 minus cosine squared theta equals. It equals sine squared theta, doesn't it? So I can come down here and say, okay, this is the same thing as sine squared theta. Bring down this equal sign, right? And guess what? The left side and the right side equal the exact same thing. All right, is that okay? You sort of understand what I'm doing here? It's tough, so we'll do a couple more examples. How about this one? Again, this is supposed to say prove, but whatever. Let's draw that line down the middle. Let's work on the left side. What do you think? Can we replace the cosine of 2 theta? Yeah, we've got 3 options, right? So let's see, I've got 1 minus, be careful here now as I go to replace it. What do you think? Well, on the right side, I have the sine squared. So what if we use the option that just involved the sine? That would be a pretty smart selection on my part, don't you think? I'm not a smart guy, but that's a pretty smart selection, because I want to make the left side look exactly like the right side. The right side has sine squared. Hey, let's use the 1 minus 2 sine squared theta for the substitution for the cosine of 2 theta. All right, let's distribute this negative here. Let's see what happens when we do that. So we get 1 minus 1 plus 2 sine squared of theta all over 2. That's kind of nice, right? Because this drops out. 1 minus 1 is 0. So I've got 2 sine squared theta over 2. Those 2's are going to drop out. And guess what's left? Sine squared of theta. How awesome is that? Yeah, that's awesome, man, because that's what I had on the right side, right? So there you go. They're equal to each other. So I got the left side to equal the right side without crossing the equal sign. All right, how about this example? This expression is equivalent to which of those 4 choices? Well, I don't know, but let's give it a shot. So let's see here. We've got the cosine squared of theta minus, cosine of 2 theta. We've got some options to replace that, right? Hey, listen, if you wanted to, I could replace the cosine squared too, right? Remember, sine squared theta plus cosine squared theta equals 1. So if I solve for the cosine squared, what do I get? 1 minus sine squared, right? So if I wanted to, I don't really want to, I'll be honest with you, but if I wanted to, I could replace cosine squared theta with 1 minus sine squared theta, right? But whatever. Maybe I'll use it in a few steps. We'll see what happens. But first, let's deal with the double angle, cosine of 2 theta. Now I have the cosine squared here, so what if I used the option with just the cosine? All right. I don't know. I have no idea whether or not this is going to work. But let's give it a shot and see what happens here. So I've got cosine squared of theta minus 2 cosine squared theta. All I'm doing is distributing the negative sign here. All right. Distributing that negative sign to the 2 terms. And what happens here? Well, this is 1 cosine squared minus 2 cosine squared, which is going to be a negative 1 cosine squared theta plus 1. All right. I don't really need the negative 1. I could just write this as negative cosine squared theta plus 1. What do you think? Is that an option? It sort of almost looks like 3 or 4, right? But it's not. That's a bummer. What do you think here? I've got cosine squared and I've got 1. Cosine squared and 1 up there. What if I went back to this formula here? Sine squared theta plus cosine squared theta equals 1. And what if I solved it for the sine? Right? So if I solved it for sine squared of theta, I'd get 1 minus cosine squared theta. Guess what? 1 minus cosine squared theta equals sine squared theta. That was a tricky one. That was a tricky one, right? Because it's cosine squared. This is cosine squared, negative cosine squared theta plus 1. That is the same thing as 1 minus the cosine squared of theta, right? The 1 is positive, the cosine squared is negative. They are the exact same thing, right? And that is the exact same thing as sine squared. That was a tough one. That was a good one. These are all good ones. The tougher they are, the better the questions are. It's just meant to challenge you there. All right, how about number 5? What do you think? Sine of 2a, that's a double angle formula. You've got one option here. This is going to be 2 times the sine of a times the cosine of a, right? That is your only option. Minus 2 sine of a, there's nothing we can do with that. If you ask why is there nothing we can do with that, this is not a double angle formula. The angle is just a, right? Here we doubled the angle. Here it's a single angle. All right, so we don't have any formulas for single angles. All right, so that's what I've got. I'm looking at the 4 choices. I have no idea. All right, so let's come back to this. Is there anything we can do? Maybe I could factor out a 2 and a sine of a, right? It looks like both terms have a 2 and both terms have a sine of a. So if I factored that out, I'd have the cosine of a minus 1 that is left. That kind of looks like that one, doesn't it? Yeah, it does. That is choice 4. All right. Let's try another one. Why not, right? These are so much fun. Just a couple more. Hang in there with me. All right, so prove. So this is a trig identity, so you sure want to put that line down the middle. What do you think? What are we going to do with this here? No idea. But we do have a formula for sine squared, right? Remember, sine squared theta plus cosine squared theta does equal 1. If I solved for the sine squared, I'd get 1 minus cosine squared theta. So I could replace sine squared theta with 1 minus cosine squared theta, right? Let me just keep all this other stuff here in black because all I'm changing is the red. All right. And I'm not going to touch this right side, okay? This right side I'm just going to sort of bring down, and I'm going to hope that I can establish the left side as being 1 plus the cosine of theta. We'll see. All right, so let's keep going. What am I doing now with this fraction here? It is a fraction. What's going on up top? 1 minus cosine squared. That's the difference of 2 perfect squares, isn't it? Up top here is kind of like x squared minus 9, right? That's the difference of 2 perfect squares. X plus 3 times x minus 3 is how I would factor that. Could I factor 1 minus cosine squared? That's kind of the same thing as factoring 1 minus x squared. What's that? That would be 1 plus x times 1 minus x, right? So let's factor 1 minus cosine squared. So that's going to be 1 plus cosine of theta times 1 minus cosine theta. Okay, I'm going to keep the bottom the same. If you wanted to, you could pull out a 1 on the bottom or put it in parentheses, and guess what? These guys are now going to cancel, and look at what's left. I've got 1 plus the cosine of theta, and that equals 1 plus the cosine of theta. Huh? So, good times, good times. We did it. We proved it. All right, they are such good times that we'll do one more. All right, what do you think here? Prove 1 plus the secant equals cosine of theta plus 1 over the cosine. Well, this is a bummer because there are no double angle formulas or no Pythagorean. There's no sine squared or there's no the sine of 2 theta. So what do you think? You want to go with the left side? You want to go with the right side? What do you want to do? It really is completely up to you. I guess I'll go on the left side here and I'll do 1 plus. I've got to rewrite secant. What do you think? I have cosines over here, so maybe I should rewrite the secant as 1 over the cosine, right? And now I've got 1 plus 1 over the cosine, which is really 1 over 1 plus 1 over the cosine. I've got two fractions that I'm adding, right? Can I get common denominators? What if I multiply the top and bottom by cosine of theta? I'd have the cosine of theta plus 1 all over the cosine of theta, wouldn't I? Yeah, what's going on over here? Yeah, that's the same thing, right? So bring this down, and guess what? These guys are exactly the same. I have proven that they're equal to each other. All right, so that's the story there. It's such a good story. We'll do one more. I'm sorry. I think I told you that. The last one was the last one, but this one I promise is going to be the last one. What do you think? We're looking to prove it, so we're going to draw a line down the middle. I usually choose to work with the more complicated side. I know that sort of sounds crazy, but that's usually what I do. So I'm going to leave the tangent alone, and I'm going to rewrite the secant as 1 over the cosine. All right? And then I'm going to write the cosecant as 1 over the sine. All right, that doesn't look like tangent, but whatever, it's something. Now I've got a fraction divided by a fraction, so guess what I could do? I could keep the first fraction, change from division to multiplication, and I can now flip the second fraction. So now I've got sine over cosine. Yes, 1 times sine is sine. Cosine times 1 is cosine. And of course, the tangent is the sine over the cosine, right? So I could say, hey, this equals the tangent of theta. Bring this stuff down here and say that also equals the tangent of theta. That's it. Mission accomplished. All right. All right. I told you that would be the last one. So that's it. Hopefully by now you can reproduce these 3 Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. Tan squared theta plus 1 equals secant squared theta. And 1 plus cotan squared theta equals cosecant squared theta. Yes, you have to remember those. Sorry about that. But remember, they all come from sine squared theta plus cosine squared theta equals 1, all right? You could get these other two just by dividing both sides of the equation by cosine squared theta to get this guy, or dividing by sine squared theta to get that third one. All right, hopefully the second thing you can do is reproduce the double angle formula for the sine. Remember the sine of 2 theta is 2 sine theta cosine theta. Hopefully you can reproduce the 3 double angle formulas for the cosine. All right, cosine of 2 theta equals cosine squared theta minus sine squared theta. That's if you want something with all, no, with both sines and cosines. Or if you just wanted things in terms of cosines, you could rewrite the cosine of 2 theta as 2 cosine squared theta minus 1. Or if you just wanted it in terms of sines, you could rewrite the cosine of 2 theta as 1 minus 2 sine squared theta. All right, and hopefully you can use the trig identities up above, right? These 3 for the cosine of 2 theta, that one for the sine of 2 theta, and these 3 Pythagorean trig identities. Hopefully you could use those trig identities above to prove that equations are equivalent. All right, so that's it. If you can't do those 4 things, don't worry. We'll get plenty of practice in class. And hey, you know what? You could always watch this video a second, a third, or a fourth time. But thanks for watching.